last class we found out the relation between the omega slip and the quadrature axis current, that is IQS, in the field oriented reference frame, that is when the DQ axis is oriented along the flux space phasor. So, when we found when the D is along the flux space phasor, the imaginary component psi QR is equal to 0. So, d by dt psi QR is equal to 0. So, from the rotor circuit, d by dt psi QR is 0, then the voltage coming across the RR is the rotational voltage. So, that we equated. Then we found the IQR in terms of IQS, that is from the flux equation. Then we found omega slip is equal to proportional to IQS. Okay, so under field oriented control, omega slip is proportional to IQS, and we know that for a motor the torque is proportional to slip. Now let us take the D axis equivalent circuit under field oriented control. So we will go to the next page, that is the D axis equivalent circuit. Equivalent circuit. In the D axis equivalent circuit, the psi dr is our psi r, flux phasor magnitude, correct. Now let us know the D axis equivalent circuit, and from there we will derive the relations. This is mutual inductance, okay. This is BDS, okay. This is psi ds, that is psi ds which couples this mutual and the leakage. Leakage is equal to LS. This is mutual, psi ds. This is the rotational voltage term that we have derived previously. This is equal to omega s minus omega r into psi QR, okay. This is IDR. Now in this equation, psi dr is equal to psi r. What is psi dr? Psi dr is equal to, that is this one, psi dr, which couple the leakage, rotor leakage and the mutual inductance, that is equal to, this is IDS. So psi dr is equal to m into IDS plus LRR IDR, okay. See, LRR is at the term, LRR is mutual plus leakage LR, okay. So leakage we can always in induction motor equivalent circuit, leakage is represented as a fraction of the mutual inductance. So this we can write as m into IDS plus m into 1 plus sigma r. Sigma r is the fraction, 5% of the mutual inductance. So the sigma r is a fraction, it's a constant, into IDR, okay. This is our psi dr. So if you see here, this flux is the combination of inductance plus current, and we want this flux to keep the flux constant under field oriented control. So let us say constant means now IS we have to split along the dr and perpendicular to that one. Then as I told, when the parallel component, the component along IDR is kept, when it kept constant, the flux psi dr or psi r is constant, because now psi r is along dr axis. So let us say the current which is responsible for the rotor flux, we can write as M into IMR. This is from this equation. This is equal to M into IDS plus 1 plus sigma R into IDR. Okay. So, from this equation, the IDR, which is very difficult to measure because we want all the quantities in terms of the starter quantities. So, IDR is equal to IMR, the flux producing component, minus the starter IDS by 1 plus sigma R. Okay. Now, let us go back to our rotor side, d-axis rotor side. If you see here, psi QR is equal to 0. Okay. Under field orientation, psi QR is equal to 0. Now, dr we are keeping constant. So, the d by dt psi dr. So, what is the current? So, what is the voltage coming across IDR? IDR is equal to, or sorry, to the resistance R is equal to d by dt psi dr, because psi QR is equal to 0. So, now if you write down the voltage loop equation here, d by dt phi dr plus RR IDR is equal to 0. Okay. This voltage loop equation. This is equal to, now psi dr we put as psi dr is equal to, this is psi dr, M IMR. So, d by dt, he can write it here, M into d by dt IMR, that is our psi dr, that is we have got from this equation, that is this equation. So, this is equal to psi dr. So, d by dt psi dr, that is this one, is equal to M into d by dt IMR plus RR IDR, that means plus RR by 1 plus sigma R into IMR minus IDS is equal to 0. Okay. This we can multiply throughout by 1 plus sigma R into RR. So, this will be equal to M into 1 plus sigma R divided by RR into d by dt IMR is equal to plus IMR is equal to IDS. This is the equation we get. What is M into 1 plus sigma R? M into 1 plus sigma R is equal to LRR. This is LRR, that is mutual plus leakage. So, LRR by RR is the rotor time constant. Okay, rotor time constant, that we can take as TR into d by dt IMR plus IMR is equal to ISD. So, if you see here the IMR is equal to ISD when the flux is constant, that is when TR d by dt IMR is equal to 0. Okay. When the flux is kept constant, IMR is equal to ISD. When phi dr is constant, d by dt IMR is equal to 0, IMR is equal to ISD. Then why this first order equation happens? This is valid during the field weakening region when we slowly reduce the flux. So, when you slowly reduce the flux, the ISD and the flux, the variation is proportional to the first order thing. Otherwise, in the not in the flux weakening region, that is in the constant torque region, IMR is equal to ISD, that is below the base speed IMR is equal to ISD. So, this condition we got. Okay. Now, we got the two equations. See, we have to control, we are injecting current IS into the machine. Okay. And the IS we have split into two orthogonal components. ISD into IQS, and ISD is placed along the phi r rotor flux axis. If that is correct, the perpendicular component is proportional to slip, and that will be proportional to torque, and the parallel component along the psi r is the one which is responsible for the flux. So, the both equation under field oriented control, the right equations, the current equation under field oriented control are, let us write out the previous equation, omega slip into psi dr is equal to, we got in the last class, MLR IQS into RR. Now, if you see here, psi dr is equal to omega slip into M IMR is equal to M by LRR IQS into RR. Okay? Again, M IMR, M we can cancel here in this equation. So, MM goes. So, what is omega slip? So, the final omega slip equation is equal to, omega slip is equal to IQS divided by, see, RR by LRR, that is 1 by TR. So, that is TR, rotor time constant, into IMR. Correct? IMR is equal to IDS when the flux is kept constant. So, omega slip is proportional to IQS. So, we got the correct conditions for field oriented control. Okay. Now, let us see under field oriented control how the machine, how the equivalent circuit, how the machine works, machine model. If the field oriented control is correct, the machine model is like this. See again, let us write, our condition is IMR is equal to ISD, omega slip is equal to IQS divided by TR IDS. Okay? Now, what we did, we put the, if you see our reference frame, so our reference frame, if you see here, this is our alpha, this is our beta, okay, that we are transferring to a general rotating reference frame. That is our D, and perpendicular to that one is the Q. So, the reference frame axis is always be placed along the phi r axis, phi r flux space phasor. So, this is rho, instantaneous angle. This is also rho. Okay. Now, if you know the ABC component, we can find out the alpha beta component. See, we will be measuring IA, IB, IC. From IA, IB, IC, what is alpha beta component? We know that I alpha is equal to 3 by 2 IA. I beta is equal to root 3 by 2 IB minus IC. Okay. So, alpha beta component, how do you get D and Q? Provided rho is known. Rho is means the instantaneous position of rotor flux is known. Now, under field oriented control, rho is the instantaneous position of the rotor flux. Of the rotor flux. So, now for field orientation, we have to find out the ID and IQ. So, now our ISD is equal to I alpha cos rho, that is I alpha cos rho into plus I beta sin rho. From this equation, from this figure, I beta sin rho, this is beta axis. I beta sin rho, that is this perpendicular, I beta sin rho is this axis. This is our I alpha from here. Now, ISQ is equal to I beta cos rho and this is and minus I alpha sin rho, so that is minus I alpha and sin rho, minus I alpha sin rho. Okay, that is from here we can find out. See, I alpha into cos rho is component along this one. Now this is I beta into sin rho, this is also rho. So I beta into sin rho is also equal to, because this is parallel to, perpendicular to this one is also parallel to this one. So we can get this one. Now from this one, how do you find out the equivalent circuit? Let us try to draw the machine induction motor model under field oriented control. Okay, we will draw the induction machine model when the correct field orientation is achieved. So we are sending the three-phase currents to the motor, that is the IR, then IY, and then IB. Okay. This inside the machine, if the field orientation is correct, the correct model under field orientation is, this is 3 by 2 IR is equal to I alpha. Okay, and root 3 by 2 IY minus IB is equal to I beta. So we got the I alpha and I beta. Now, if the raw information is correct, if you know the rotor flux position, instantaneous position of the rotor flux, rho is known, then using this transformation, cos rho plus sin rho and cos rho minus sin rho, we will get ISD and ISQ. ISD and ISQ. See, ISD will be equal to I alpha plus I beta into sin rho, and ISQ is equal to I alpha cos rho minus I beta sin rho. From the phasor diagram we can derive this one. So we will get ISD and ISQ. Okay. So this ISD, we know that ISD IMR tau d by dt of IMR plus IMR is equal to ISD. Okay. So from this equation, IMR, when ISD pass through a first order filter, you will get IMR. So here, this one, IMR is equal to ISD by 1 plus S tau R. From this equation, you will get IMR. The moment IMR is there, the torque equation we have derived. Torque is equal to 2 by 3 m by 1 plus sigma r into IMR into ISQ. IMR into ISQ. Okay. ISQ we got here. This torque equation, this is MD. Okay. Driving torque minus load torque. This is the load torque. We know the how to relate the speed and the driving torque and the load torque, this equation we can use md minus ml is equal to j, moment of inertia d into d omega by dt. So this we can multiply by 1 by j, a gain function. Then we can integrate it. Here you will get omega mechanical speed multiplied by p by 2. P is the number of poles. You will get the omega r. Okay. Now, from ISQ and ISD, we know if the slip is equal to, if field orientation is correct, slip is equal to ISQ minus TR ISD. So ISQ is available here. So omega slip is available. Omega slip plus omega r will give omega s. That is the speed of rotation. When you integrate, you will get rho. That is the rotor flux position. This rho we will feed it here, so that from the lookup table we can generate cos rho sin rho. So if the field orientation is correct, this is the machine model under field orientation. Okay. So let us try the block diagram for field oriented control. Block diagram. Field oriented control or vector control. See, we are giving the omega m speed reference. See, omega m speed reference. Okay. This we will give it. So there should be a feedback, omega m feedback. That we can take it from TACO, or let us see. Now, whenever there is a difference between the reference and speed, that means what it indicates? The driving torque is not equal to the load torque. So that means we have to give the correct driving torque. That means it will point to the torque means it will point to the ISQ. So here you have a controller. We will use, let us say we are using PI controller. PI controller with saturation limit should be there. That depends on the machine, how much ISQ plus or minus we can give it. So here you will get ISQ reference. This ISQ reference, we got it. Now, let us say speed feedback. So speed feedback, if you give it, till base speed will make our ISD constant. After that, field weakening, it will make it inversely proportional this way. So this is our, we have a lookup table here. This is our ISD. ISD is equal to IMR. This again will will compare with the feedback current. So this is flux reference. So this is not ISD, this is our IMR. So here again we have a PI controller. This PI controller, if feedback IMR and reference IMR and feedback IMR is correct, then this will be equal to our ISD reference. Okay. So we got ISQ and ISD reference. So now we can do the inverse transformation, that is dq to alpha beta. dq to alpha beta, again we can go alpha beta to ABC. So, we will get the required IA reference, IB reference, IC reference. Okay. This we can give to our hysteresis controller. Hysteresis PWM controller. Okay. And inverter, and finally to the motor. This is our hysteresis PWM controlled inverter. Okay. Now, see alpha beta, see here PW you require reference feedback current also required. So, we can sense this current. You know IA plus IB plus IC is equal to 0. Okay. From this one we can find out actual IA, IB, IC, feed it here. Again here IA, IB, IC coming here. Okay. See one thing what we want, see dq to alpha beta, and this one you require rho here. How to get rho, we will come to that one now. See assuming rho is available, see this 3-phase current, again we are converting ABC to alpha beta, we will convert it. Then alpha beta to, provided D is known, rho is known, we will find out alpha beta to dq. Okay. So, dq we got. dq, this is ISD, actual current ISD, this is ISQ. When we pass through 1 plus STR, we will get the correct IMR, that you feed it here. Now, ISQ you got it. Okay. We know the equation, ISQ divided by IMR tau, you will get the slip. Okay. This slip, you use a tacho for the machine. From the there you can get omega r. Here you will get omega s. You integrate, you will get rho. That rho you feed it here. Okay. Now this omega you can give as a feedback here also. So our vector control is correct. Initially current hysteresis controller we can use it because it will give fast response. So high dynamic performance application we can use this one. This is the block diagram for a field area control using current hysteresis PWM control. We can use also space vector PWM also. Then we can, from the current PA control, we have to get the required voltage control. Okay. So this way we can get the field oriented controls. Block schematic for the field oriented control is like this. So this we can simulate using MATLAB and Simulink. Okay. Before an actual implementation is being done. So this is current hysteresis controller. Now if you want to use voltage control, how it can be done? See, we got the field oriented control now. Now how do you design your controller? For the separately excited DC machine, we have found out some set of rules to find out the PI controller. So let us draw the closed loop schematic. From there, same techniques what we use separately excited DC motor, we can use it here also. So let us see the closed loop controller block diagram. See, you have the omega reference. And this is the omega feedback. Okay. So this will give to a speed controller, PI controller. So that we will make it as K1 into 1 plus ST1 by ST1. This is the PI controller. This output will give our IQS star. Okay. This IQS star the voltage control, we are check IQS and IQS feedback. It's coming here. Okay. This will give it to current controller. That is K2 into 1 plus ST2 by ST2. Okay. This controller output will, if you use current hysteresis controller, this output IQS we can directly convert it to using IQS and IDS we can directly convert into IAS reference, IBS reference, ICS reference. But if you want to control the space vector PWM, then we require the voltage reference. So here we will have IQS reference and IQS feedback. Then one more hysteresis controller. This output will give our VQS reference. Okay. This vector we will give to a PWM converter. So converter has to be, or inverter. Inverter will again pass through, we will model as a first order lag. So we will say inverter K3 by 1 plus ST3. This is the inverter. This is our inverter. So same like our PWM, because of the PWM frequency we can find out approximately 1 ST3. So this it will go to the machine. Machine again it will be same like separately excited DC motor, 1 by RS divided by 1 plus S leakage inductance, time constant due to the leakage inductance, that is STS, we will put it. This will give the output IQS. So IQS maybe gain and filter if it is required, you have to put it here and feed it here. So this current control we can same like a current loop and out of speed loop. So this IQS multiplied by 2 by 3 m by 1 plus sigma r into IMR is our torque. This torque MD minus ML 1 by SJ, SJ the moment of inertia, you will get the speed feedback. Speed feedback again if you want a filter with a filter and gain, that first order we can model it as first order. So we will get outer speed loop and inner current loop, same like in a separately excited DC machine. And for the DQ axis, D axis, see you have the current reference. Under field weakening, it will go inversely proportional, both the forward and reverse. So this will give our, depending on the speed, our IMR. IMR reference plus minus IMR feedback. Okay. This will give to one controller, that will give our IDS reference, that is K4 into 1 plus ST4 divided by ST4. This will give our IDS reference. IDS reference minus IDS feedback. If we are using a space vector PWM, then we require VDS. So one more PI controller. So this is K5 into 1 plus ST5 ST5. This will give VDS reference. Again the converter, VDS reference, the same converter. That is the same K3 by 1 plus ST3. It will pass through one by RS. Here this is not S sigma TS, because Q axis because of the leakage time constant, that, and here this is mainly the mutual inductance time comes. So, this is 1 plus STS. TS is the starter time constant. Okay. This one starter, that mutual plus leakage, because this is the flux producing component. So, it will mutual inductance time into picture. So, this will come here, and again if you are using a filter plus again we can feed it here. This is our current reference. Now, IDS 1 by 1 plus STR is our IMR. So, this loop also we can design if you know the input output relation, same like what we use for the separately excited DC machine or front end AC DC converter, we can use this one here. So, this way we can have a vector control, we can have it. But the most important thing is the rho, instantaneous position of rho. If rho is correct, field orientation is correct, then we can use this closed loop control for block diagram for designing the control parameters. So, the most important thing is finding out the rho. As I told before, a tacho or a position encoder is required, then slip is required, slip you have to add and integrate rho will get. But if you see, the slip is depending on the TOR, that is rotor time constant. So, rotor resistance, it can vary with the temperature. So, wide variation is possible here. So, many control scheme is available for parameter adaptation, that how to control the rotor time and adaptation of the rotor time constant with respect to temperature is available. Many paper is available in the literature, but we will not be dealing that one now. See, in this field oriented control, we have used the current hysteresis controller. That means here we have the ISQ and ISD reference we generate, then using rho we convert it into I alpha I beta, then alpha beta to ABC. Then ABC current and the ABC feedback, that is ABC feedback, we will use the simple hysteresis controller. But as I told, the problem with the hysteresis control previously, it's wide switching frequency variation, okay, and optimum PWM switching is not required. So, instead of, if you use a voltage controlled converter with a space vector PWM or sine triangle PWM, then we want the reference to the PWM is not current, the voltage. Then the field oriented control scheme will be, the block diagram will be like this. We will go to that one now. Next page we will go. Okay, where the command voltage as the command variable for the inverter. So, field oriented control with the voltage as the command variable. So, here also we have the reference speed reference. This is our omega R reference. Then speed feedback is there, that will generate from encoder or a tacho. Then this PI controller output. As I told, any change in the speed, command speed and the reference indicates a difference in that torque command and the load torque. So, we have to give the correct ISQ, which is proportional to the torque. This ISQ will compare. See, now the voltage we are injecting into the machine, use PWM control, voltage we are controlling. So, we know whether the correct ISQ is coming. So, ISQ, this we will take reference, ISQ feedback is required. So, this output PI controller will give our VSQ star. Okay. Similarly, you have the speed feedback or speed reference. We have the lookup table for IMR. This is during the field weakening region. IMR will come here. During steady state of operation, IMR will be equal to ISD. So, we have the ISD feedback here. ISD. This is the PI controller. This will give you our VSQ star. Okay. So, I have intentionally put this one. There is some more time also we need to add here. So, this we will talk about later. Let us say VSQ is coming. This VSQ will go to the PWM modulator and inverter, PWM inverter and control. We require the raw signal also. So, VSQ, VSD we got it. Here we require the raw also. This it will go to the motor, induction motor. Okay. From the motor we will sense the current. All the three sensors are not required because IA plus IB plus IC is equal to 0. So, 2 current sensing is required. For clarity we have put 3 here. These are in ABC. So, we will convert into ABC to alpha beta. Okay. Again alpha beta to DQ. Here also we require raw information. This raw is required here also. Okay. So, here we get ISD feedback and ISQ feedback. We know that ISD will be equal to IMR in the steady state. If any transient flux weakening is there, this ISD by 1 plus STR, correct? This is the correct IMR. So, we will give it here. So, feedback and IMR will be the same. Now, this ISD, we know how to compute the slip information. Previous block diagram we have found slip is equal to find out slip computer. Okay. Slip, and we have the TACO. These two added we will get omega s. That integrate will get rho. Okay. This is the rho. We will be feeding it here. Okay. So, and again this feedback will close it, omega r. Okay. Now, this VSQ, VSD, this is coming from ISQ feedback. ISQ feedback here also, that feedback term we will close that one. It is coming from here. Okay. So, you will get how to compute VSQ, VSD. See, what is this one? So, any change in the ISQ and ISQ feedback immediately should reflect on VSQ. This shows, that means VSQ is dependent only on ISQ, and here this is not VSQ, sorry, this is VSD, and VSD, sorry, this is VSD. VSD we are taking from the IMR reference and ISD feedback and the PI controller. That means any change in the ISD reference and ISD feedback should reflect to VSD. But if you see the actual VSD VSQ equation, let us go back to the actual VSD VSQ equation. Here we can see VSD is equal to RS ISD plus from the original plus LSS d by dt ISD minus LSS omega s ISQ. So it shows VSD, there's a ISQ, any change in the ISQ component, it will reflect on VSD, plus M into d by dt IRD minus M into omega S IRQ. See, IRD, IRQ terms, the rotor currents we can represent in terms of ISD and ISQ. We know that one, IMR minus ISD divided by 1 plus sigma R is equal to IRD. Okay. So substituting this one here, also we know that IRQ is equal to psi RQ minus MISQ divided by LRR. Okay. And under field oriented control, psi RQ is equal to 0. So let us substitute this one and write VSD. So then VSD is equal to RS ISD plus LSS d by dt ISD minus LSS omega S ISQ plus, here we have to change IRD. IRD is equal to, that is this term, M into d by dt IMR by 1 plus sigma R minus M into d by dt ISD by 1 plus sigma R okay. Then minus M into omega S into IRQ, that is psi RQ by psi RQ minus M into ISQ divided by LRR. Okay. Psi RQ is equal to 0 under field oriented control. Okay. Also, we can say during steady state d by dt IMR is equal to 0, IMR is equal to ISD, so d by dt ISD is also 0 here. Okay, we can assume that one. So this goes. Then finally this will be equal to RS ISD, then minus omega S into LSS minus M by LRR into this M and M will come M square into ISQ. See, this LSS by LRR, this term LSS minus M square by LRR, we can write as LSS into 1 minus M square by LRR LSS. So this will become a constant, that we can get sigma LSS. So this will become sigma LSS. So this equation, that is this equation, we can effectively write as minus omega S sigma LSS ISQ. Okay. So this we will put as the feed forward term in the controller here, ISD term. Okay. So in the VSD term here, see there is a feed forward term. See, already ISQ we know it. So we can use this one omega sigma LSS ISQ here. We can feed it here. Omega yes sigma LSS into ISQ. So what is the advantage? This feed forward term, then this PI controller has to change only for any variation in the ISD only. Any ISQ variation, it will immediately affect through this one. Similarly, we can find out the feed forward term from the DQ for the VSQ. We can find out from the equation. We can the same derivation, and we can use it. See here, we will see if you go to the equation, VSQ is equal to RS ISQ plus sigma. Finally, it will come sigma LSS d by dt ISQ plus omega sigma LSS ISD plus omega into 1 minus sigma LSS or IMR. If you from the matrix term, that equations DQ model, if you get the VSQ equation, if you get finally you will get this one. See here, omega IMR is equal to ISD, correct? So sigma IMR we can replace with ISD in the steady state operations. IMR is equal to IC. Finally, this equation will be equal to RS ISQ plus sigma LSS d by dt ISQ plus omega LSS ISD it will come. Because IMR we are taking into ISD. So this term together it will come here. So this term we can use a feed forward term here. This is also plus here. This is also plus here. So here we can use the feed forward term from the ISD, that is omega S LSS ISD here. So what is the advantage? So this PI controller has to vary. VSQ has to vary only variation in the ISQ. So the variation for the PIQ is limited only due to the ISQ here, and in ISD variation we are feed forward here. So it need not come through the PI control. So it will also increase the response of the system. This way, for voltage control inverters with voltage as the variable for the PWM, we can use this type of closed loop scheme for the vector control application.